Welcome to the physics class Heat and Thermodynamics, and it is the Unit 3, the thermodynamic potentials and the Maxwell's equation. And this is the Nagabhushanam Department of Physics and the K.B.N College. And mainly in this class we covered some topics like the thermodynamic potentials, Maxwell's equations, the derivation, and the classical reference equation and applications, and specific heats, and the Joule-Kelvin effect. First of all, what are the thermodynamic potentials? The thermodynamic system is denoted by basically some the coordinates like the pressure, volume, and temperature, the entropy. But these four parameters are not given to the complete information about the system. So there is a need of some other energy functions. They are called the thermodynamic potentials, and they are four energy functions. They are internal energy, Helmholtz energy function, and enthalpy, and the last one is the Gibbs energy function. So internal energy denoted by U, Helmholtz energy function denoted by F, enthalpy H. Enthalpy is also called as the total heat energy function, and the last one is the Gibbs energy function denoted by G. So the thermodynamic potentials are mathematically they are obtained by combining the four thermodynamic coordinates or variables of pressure, volume, temperature, and entropy. And the Maxwell's equations, these four are the Maxwell's equations, and these are derived from the thermodynamic potentials. And the four equations are obtained from the internal energy and the Helmholtz energy function, and the enthalpy, the total, and the last one the Gibbs energy function. And these four thermodynamic Maxwell's equations are useful to derive the classical reference equation, and they are also useful to explain how to change the melting point at the boiling point with pressure. And one of the Maxwell's equation, and this it is the second equation, and from this second equation we derive the classical reference equation. It is T into dou P by dou T. The dou P by dou T is equal to L by T into V2 minus V1. Here dou P by dou T is the rate of change, the pressure with respect to the temperature, and L is the latent heat, and T is the absolute temperature, V1, V2 are the initial and the final volumes. So V2 minus V1 is the change in the volume. And the classical reference equation is useful to study how to change the boiling point or the melting point with the change in pressure. And it also explains the phenomena of resolution. Resolution means it is suppose there are the two ice cubes, so both are pressed together, then it combined to a single piece. It is called the resolution. And the specific heat. Specific heat. That means the amount of heat energy required to rise the unit temperature of the unit mass, and it is divided into two types. One is the CV and other one is the CP. CV means the specific heat at a constant volume, and CP means it is the specific heat at a constant pressure. And here CP is always greater than CV, because in case of the CP, the required heat energy is useful in two ways. One is to increase the additional energy, and the remaining is to do the external work. So CP is always greater than CP. So the ratio between the two specific heats is equal to ES by ET. CP by CV is equal to the gamma. Gamma means the ratio between two specific heats. Here CP is the specific heat at a constant pressure, and Cv means specific heat at constant volume. In the elasticities, it is also equal to the ratio Es to Et, where S is the entropy and T is the temperature. Es means it is the elastic constant at a constant entropy, and Et is the elastic constant at a constant temperature. And the difference between the two specific heats, and it is for perpetual gas it is equal to the capital R, where capital is the universal gas constant, and for true gas or van der Waals gas it is equal to Cp minus Cv is equal to into dou P by dou T at V. Dou V by dou T at P, it is the basic equation, and for perfect gas it is equal to R, and for van der Waals it is equal to R into 1 plus 2A by RVT. And the Joule-Kelvin effect, and it is also known as the Joule-Thomson effect. And here the gas is passing through narrow holes, that is the porous plug, from constant high pressure region to constant low pressure region. There is change in temperature. So some, except hydrogen and helium, at ordinary temperatures there is a cooling effect, but in case of the hydrogen and helium we observe the heating effect. And the fall in temperature is directly proportional to the change in temperature is directly proportional to the pressure difference between on either side of the porous plug. But at a particular initial temperature there is no change the temperature, that means neither increase nor decrease. The particular temperature is called the inversion temperature. It is denoted by Ti. Suppose T greater than Ti, that means initial temperature is greater than Ti, that is the heating effect, and less than Ti, that is the cooling effect. And for perfect gas, the Joule-Kelvin effect is the 0. For van der Waals, the formula, the inversion temperature 2A is equal to 2A by RB, where R is the universal gas constant and AB are the van der Waals constants. Thank you.